Hello, welcome to Module 9 of the GPU Teaching Kit. In this module, we're going to cover the reduction parallel computation patterns. And we're going to start with Lecture 9.1, Parallel Reduction. The objective of this lecture is to learn the parallel reduction pattern. It's a very important class of parallel computation patterns. And using this pattern, we're going to teach the concept of work efficiency for parallel algorithms. And also we're going to cover the concept of resource efficiency of parallel computation. Reduction is a computational method that is often used in a partition and summarize strategy for processing large input data sets. In order to apply such a strategy, there has to be no required ordering of processing elements in that data set. That is, the computation we need to do on the data set has to be both associative and commutative. With this strategy, we will first partition the data set into smaller chunks, and then we have each thread to process one or a small number of these chunks. And we use a reduction tree to summarize the results that are generated by each chunk and summarize them into the final answer. Examples of such strategies are supported by Google and Hadoop MapReduce frameworks. And these frameworks are often used by data analytic users to process very large data sets. And for this lecture, we will focus on the reduction tree step. Reduction is also used to enable other techniques. For example, we can use reduction to clean up after some commonly used parallelization transformations. A very good example is privatization. We may have a computation where multiple threads write into a single output location. And these multiple threads, when they write into that location, they will conflict with each other and serialize each other's execution. So we're going to replace the output location so that each thread has a private output location, and this is the privatization idea. Once we complete the execution of these threads, we use a reduction tree to combine the values of the private locations into the original output location. So now, what is really a reduction computation? The reduction computation summarizes a set of input values into one value using a reduction operation. And the reduction operation could be max, min, sum, product, and so on. And all these operators need to be associative and commutative. So all the four examples that we have here are associative and commutative operators. And they have to have a well-defined identity value. That is, for sum, 0 is that identity value. 0 plus anything gives this other thing. And so anything plus 0 will only give itself. And we can definitely have similar identity values for max, which is the negative infinity, and min, which is the positive infinity, and product, which will be value 1. So we could also have a situation where the users may supply a custom function for calculating reduction, and these functions, as long as these functions come with a identity value, and the execution of these functions are associative and commutative, we can just use that function as the reduction operation. In general, reduction is part of a family of operations called collective operations. In large parallel systems, we have these collective operations that would essentially be used to produce some kind of collective result of a large number of parallel execution threads. Before we look at parallel reduction operations, we need to first look at a sequential reduction algorithm. Here we look at a efficient sequential reduction algorithm that has an algorithm complexity of order n. For this sequential algorithm, we first initialize the result as an identity value for the reduction operation. If we're using the max reduction, we will use the smallest possible value in the system, and mathematically that will be negative infinity. And the largest possible value for the mean reduction in the system, and a 0 for a sum reduction, and 1 for a product reduction. And then the algorithm will iterate through the input and perform the reduction operation between the result value and the current input value. And for example, if we're using a max reduction, we will compare the current result, the current input value with the result up to this point. And if the current input value is greater than the result that we have so far, then the input value will replace the value in the current result. So we would visit all the input values and perform this kind of operation. And so we would perform n reduction operations for n input values. And each input value is only visited once. So this is an order n algorithm, and this is a very computationally efficient algorithm. Now we can look at a parallel reduction algorithm. Here we show a parallel reduction tree algorithm. And this parallel reduction tree algorithm will have levels of parallel operation. At each level, each operation will operate on two input values. So here we show an example of the tree reduction algorithm for maximal, calculating maximum. At the first level, we have four parallel operations, each calculating the maximal between a pair of input elements. And then we produce four output elements from these parallel reduction operations. And the next level will have two operations, each produce a maximal value out of a pair of the temporary output values produced by the previous operations. And finally, we have two values that will be compared in the last value, and we produce the maximal value among all the original 8 values. And if we look at the information flow within this operation, which is shown in the slide, we see that it has a tree shape, and then all the operations are being, all the values are being funneled towards the root, which is at the bottom of the tree. And we can see that in order to process 8 elements, we will be executing 7 reduction operations. And so this is a parallel algorithm that will perform n-1 operations on n input elements. And we can perform the parallel operations in 3 steps when we process 8 elements. And in general, we will be performing log n steps when processing n elements. And this is where the speed up is going to be for parallel computation, because instead of doing 8 sequential compare and swap operations for this max reduction, we will be doing log 8, which is 3 steps. And this will give us a much faster execution when the data set becomes big. Real life, we use a reduction tree for for many logistics. For example, here we show the final schedule of the World Cup, and in one of the World Cups, which was held in South Africa. And here we show the final 8 teams, and then at the outmost the purple tabs, we show the 8 teams, and then each of them will pair up and have a game so that we produce 4 winning teams. And then when we work towards the middle, we have 2 winning teams, and in the final we have 1 winning team. So each game is really a reduction operation. It's a max operation. The one that prevails will advance to the next level, and then we have continue to have these reduction operations until we produce a champion, which is the max of the original 8 inputs. So when we do a quick analysis of the reduction tree parallel algorithm, for n input values, we will be performing n-1 operations. This is because at the first level, we're going to use half n of parallel operations, and the second level will use 1/4 n of parallel operations, and then the next level will use 1/8 of n of parallel operations. If we add up the series of 1 plus half plus 1/4 plus 1/8, it becomes 1 minus 1/n. And for n that is very big, and so it was approach n, but for any particular n value, this series adds up to n-1 operations. And should be also very clear that the parallel computation will perform log n steps. So because when we look at the number of operations, by the log nth level, we will have only 1 operation, and that's the end of the computation. And if we have a million input values, because of the log n, we will only need to take 20 steps to finish the computation. So this is a very, very fast parallel computation, and compared to the 1 million steps of the sequential computation. But this assumes that we have enough execution resources. Remember, if we want to be able to complete the execution in 20 steps, we actually have to have 500,000 comparisons all done in parallel with each other. So if we calculate the average parallelism throughout the computation, we have n-1 operations done in log n steps. So for n equal to 1 million, the average parallelism will be 50,000. However, the peak resource requirement will be 500,000, which is needed to do the first step. So this is not a very resource efficient algorithm. And we're on average we're only using 1/10 of the resources. Another important analysis on the algorithm is the work efficiency. We say that this is a work efficient parallel algorithm because the amount of work done, the total amount of work done for the data set is comparable to an efficient sequential algorithm. Remember, in the sequential algorithm, we have order n, and here the total number of operations we do throughout the computation is also order n. So this is why we say that this tree reduction algorithm is a is a work efficient parallel algorithm. And many parallel algorithms are not work efficient. So we will be looking at this issue in much more detail through this lecture as well as other parts of the course. One important point to remember is that an algorithm can be work efficient, but may not be resource efficient, as we illustrated with this slide. This concludes lecture 9.1 of the GPU teaching kit. Thank you.